Hi friends, welcome to my channel Path of Physics. Today in this video I am going to discuss about least disk method. It is used to measure thermal conductivity of a poorly conducting material such as wood, glass or polymer. It is a steady state method. Steady state method means steady state methods are ones where the experimental setup must reach equilibrium before any calculations can be made. Steady state method means consider a metal bar. If it is heated for some time, after some time, each part in that metal bar measures constant temperature. The temperature won't change with time. So that condition is called steady state condition. Now, next we are going to discuss about the experimental setup. Two metal discs, usually brass, a steam chamber, the specimen whose thermal conductivity is to be measured are taken. Specimen should be in thin disc form with size same as metal disc. Then two thermometers are required to measure temperature gradient. Thermometers are inserted into the metal disc. The specimen is placed between two metal discs. Steam chamber is placed on top of the top metal disc. The whole setup is suspended in air. So any other conduction effects are removed because air is an insulator, right? Here is what an I have. Here is an illustration of the experiment. This is a steam chamber, this is the steam inlet, and this is the steam outlet. Steam passes, water is boiled, and steam is allowed to pass through this chamber. So, due to this, the steam chamber gets heated up, and this heat is conducted to the top metal disc, and from there to the poor conductor, then to the bottom metal disc. Step 1. Water is heated and steam is produced. It is allowed to pass through steam chamber. This causes conduction of heat from steam chamber to the bottom area. Heat passes through top metal disc, poor conductor and bottom metal disc. Bottom metal disc is otherwise known as least disc. So I have explained it before. Now next coming to step 2. After some time steady state is reached. I told what is steady state. The temperature readings of T1 and T2 thermometers become constant. T1 and T2 are the thermometers inserted on these metal discs. So the readings T1 and T2 show the readings shown by T1 and T2 remains constant after reaching the steady state. Let that readings be theta 1 and theta 2 respectively. At steady state, the amount of heat transferred from poor conductor to bottom disk is equal to the heat lost by that disk due to conduction. At steady state, the amount of heat coming here, amount of heat conducted by this poor conductor to the bottom metal disk is the amount of heat lost from due to convection from this bottom metal disk. Heat loss happens from here and from this side also. So quantity of heat conducted by the specimen per second is Q is equal to Ka theta 1 minus theta 2 by D. This is given by law of conduction. K is the thermal conductivity of the specimen. A is the area of the specimen. Theta 1 minus theta 2 is the temperature difference. Theta 1 minus theta 2 by D is the temperature gradient. D is the thickness of the specimen. Now quantity of heat lost by bottom disk, it is also equal to Q, and Q is equal to mc d theta by dt, where m is the mass of the bottom disk, least disk, and c is the specific heat capacity, into mc d theta by dt times fraction of area from which heat is lost. So next we have to find fraction of area from which heat is lost through bottom disk. It is equal to bottom base area plus curved surface area. Bottom base area means, see, heat is lost from this bottom base area and from also from the curved surface area. Okay, this from this part heat is coming. It's not going out where it is not going outside. So bottom fraction of area is bottom base area plus curved surface area by total area. It is given by pi r square plus 2 pi rh by 2 pi r square plus 2 pi rh, where r is the radius of the least disk and h is its thickness. Now it is this is equal to r plus 2h by 2 into r plus h. Now substituting this value in equation 2, we are substituting this value in this equation, we get q is equal to mc d theta by dt into r plus 2h by 2 into r plus h, where m is the mass of the least disk. It is weighed using common balance, and c is the specific heat capacity of the least disk or the bottom disk. Now if you are looking, if you found out something, equation 3 is equal to equation 1. See, its LHS is equal, LHS is q. See this equation 3 and equation 1. See, both the LHS, it is q. Both are equal, both the equations are equal. So we can equate equation 3 and equation 1. So equation 3 equals equation 1. So we can equate the RHS. So it becomes Ka times theta 1 minus theta 2 by d is equal to mc d theta by dt into r plus 2h by 2 into r plus h. In next step, we are putting the value of A here. A is the area of the specimen. It is pi r square, where r is the radius of the specimen. K into pi r square into theta 1 minus theta 2 by d is equal to mc d theta by dt into r plus 2h by 2 into r plus h. This is the fourth equation. Now in step 3, we have to find d theta by dt. Other all constants, other all terms are known. Only d theta by dt is unknown. So we have to find d theta by dt. It is actually rate of cooling. Rate of cooling of the metal least disk. To find d theta by dt, the steam chamber, the top metal disk and poor conductor is removed. Then the steam chamber is then kept on top of least disk and is heated till temperature reaches theta 2 plus 10 degrees Celsius. After that, steam chamber is removed. Then the least disk is allowed to cool. For every 1 degree change in temperature reading of thermometer, and time is taken. For every 1 degree change in temperature reading of thermometer, temperature is noted and time is also noted. Then readings are taken till temperature reaches theta 2 minus 10 degrees Celsius. A cooling curve is plotted with the data, with temperature on y-axis and time on x-axis. Then temperature theta 2 is located on the graph. A tangent is drawn on the corresponding point on graph, and slope is calculated. This gives the value of d theta by dt. See, this is a graph. This is the cooling curve. Here theta 2, I have marked theta 2, the corresponding, and I have also marked the corresponding point on the graph, S, and I have drawn a tangent passing through this S. Then I have calculated the slope. Slope is d theta by dt. So this gives the value of d theta by dt. On substituting this in the uh, the above equation, in our equation number 4, we get K is equal to mc pi r square d theta by dt into r plus 2h by 2 into r plus h into d by theta 1 minus theta 2. From equation 4, I have derived the equation for K, and this is how the last equation is obtained. So we got all the values. We got d theta by dt and we know all other constants. So this is the required equation for thermal conductivity of the specimen. So that's all for today. If you have any doubts, please comment on it. Thank you.